Alright, so it says Ariel works in the marketing department of a major retailer. Her job is to set prices for new products sold in the stores. She has determined that a certain product has the following function, where its profit and product price are given based on the curve. So the curve's equation is negative 6p squared plus 192p minus 1,440. She can determine the price range by finding the prices for which the profit is equal to 0. This can be done by finding the solution of the related quadratic equation. So right now we have negative 6p squared plus 192p minus 1,440. I have it graphed on that profit function to the right. So one of the things that you would want to know is which direction is the parabolic curve open? How do we know this? What indication do we have? So the graph is open down. We know this because the A value is negative. And the indication from the curve is that we have a maximum. So the other indicator is that the graph has a max. What item price would yield the greatest profit? So the greatest profit, if that's a profit curve, is going to be at our maximum. So again, if that is the profit function, the greatest profit would occur at the max. The price of that would come from your x. So the price is the p, which is our x. So that comes from the max on the curve. The max on the curve is the vertex. So if you wanted to know the x value of the vertex, that could also go back to your negative b divided by 2a formula. So if the graph wasn't given to you, you could also find that point algebraically. So it would be that negative 192 divided by negative 12, which gives you a positive 16. So the item price that would yield the greatest profit is $16. It appears from the given graph that our function has a profit of 0 at which two price points. So there are 2 price points on our curve in which this is going to have a profit of 0. And again, it looks like my numbers got a little glitchy whenever it moved into here. So like that tick mark is 4, 8, 12, so on and so forth. So if you couldn't see them from the graph, what could you do to find them algebraically? So if this 16 represents the middle of the curve, we know that these points have to be an equal distance to the left and to the right. We also know that those points have to occur when negative 6p squared plus 192p minus 1,400, plus 1,440 equals 0. So you could reverse FOIL and factor it, and that's what we're going to get 2 and 5-3. But in the case of your graph, your points are a little bit nicer looking than this. So we see that it is, maybe not, we see what? Or what could you do if you weren't sure? So like right now, it kind of looks like it's at 12. So how could you verify that 12 is where it's equal to 0?
Well, 12 is the feet, so you can...
Perfect. So you could plug 12 in here. Let me erase and remove. You could plug 12 in for P, and if it is the correct point, it should equal 0. So it would be -6, 12 squared, plus 192, dash 12, minus 1440. And is in fact 12. And then my other point is at 20. And again, you could confirm by plugging 20 in to P and making sure it equals 0. Now it's kind of 3A, but I knew I was going to be able to write it down below. So that is one application of quadratics and using them. If you take physics next year, you're in physics this year, then we use quadratics a lot to talk about velocity, talking about throwing an object up, having that object come back down. So you'll see like lots of examples using quadratics and their properties with throwing a ball. So you can do it with like shooting a basketball. You could say, okay, how high does it have to be to go through the hoop? And then you can determine if somebody's shot goes through. And those are just the applications of quadratics kind of using physics. In physics, you would call a quadratic function a velocity curve. So in example number 1, this goes back to what we talked about yesterday. If you have x's on both sides, you always want to get it to standard form with all the x's on the right side. So if we have x's on both sides, we want to manipulate the equation to be in standard form with all the variables on the right side. So that means we're moving the 10x to the right. And then we want to get it in standard form. So you want x squared to be first. Then your linear term, so the negative 10x. And then the constant, or negative 25. The y-intercept is the c value. So in this case, my y-intercept is at 0, negative 25. My curve is going to be symmetric about the point x equals 10 over 2a. Or negative 5. The vertex is going to come from plugging that negative 5 back in. So negative 5 squared is 25, but then you multiply it back by the negative 1. So you have negative 25. A negative times a negative gives you a positive 50. And then subtract 25 again. So negative 25 plus 50 minus 25 gives you 0. So this graph goes through the point negative 5, 0. So this is the case in which the vertex and the root are the same. And then this graph is reflected, but it's not stretched or shifted up or down. So it's all the parent function points, but negative. So 0, -1, -4, -9, etc. So again, whenever the vertex is on the x-axis, we refer to that as a repeated root, because what's happening is x is equal to -5 twice. It's equal to -5 twice. Like I said, we're going to go back to factoring next week. So if you were to actually have factored this, what would happen is that when it factors as the same factors twice. So we call that a perfect square trinomial. So when you have a perfect square trinomial, you will have a repeated root. Or a case of that will be a repeated root. Repeated roots can occur on other formulas, but they will always occur on those formulas. Okay. And then we have f of x equals -3x squared. So this is another case where my graph is not moved up or down. It is simply stretched or compressed. So that -3x squared is going to shift my graph in no way. My vertex is going to stay at 0, 0 because the h is at 0. My y-intercept is also going to be at 0. So this is a case in which your y-intercept, x-intercept, and vertex are all at the same point, which means my roots are at the same point. The -3 is going to reflect my graph and stretch it down by 3. So all my perfect squares are going to get multiplied by -3. So that 0, 1, 4, 9, 16 all get multiplied by -3. So this graph is very, very narrow. And once again, I have a single repeated root. I have a single repeated root. So last night, as you were graphing, some of our graphs did not have these perfect pretty roots. They had these roots that were occurring, but they were occurring at values that were not so nice. They weren't your 0, 0 or 1, 0. They were between whole numbers. So a value between a whole number is still a root, and we're going to learn how to get those exact values in 5-4, maybe 5-5. So for now, what we're going to do is if in our table or on our graph, we don't see a 0 in the y values, we are going to identify the roots as living between two of the x values. So if we don't see that perfect 0, we're going to say that our root lives between two values. So oftentimes when you're graphing, those exact roots are not there. So we're going to estimate our solutions by listing the integers, which are the whole values of x, to the left and to the right. So when a function is positive on y, and then it transitions to a negative, that is how you identify a root. Because in order for a number to go from a positive y value to a negative y value, it has to cross the x-axis. So if a number is positive on y and then it's negative on y, it had to hit 0 somewhere in between. On the opposite end of that same thought process, if a y value is negative, and then its next y value is positive, then it must also have crossed the y-axis. Or sorry, the x-axis, meaning y was 0. So looking at that table, positive, 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 positive y values. And then here I have a negative y value and a negative y value. So what you're looking for is, as you read the table left to right, for it to go from a positive to a negative, or a negative to a positive. And that happens twice. So it goes from positive 3 to negative 6, which means between negative 2 and negative 1, there was a root. So there is a root between x equals negative 2 and x equals negative 1. It's important that you list the x because it's not the y's that it's between, it's the x's. That means here that there is a second root between 0 and 1. So positive integer values that it lies between. If our table, like let's say our x vertex value is a 0.5, then you could do like between the two halves. Because if your table is halves, then you could do them as halves. Or you could look at the integers from the graph. So like those ones I kind of am more flexible with our answers. Does that make sense? My table's still up. No, that was useless. Okay. So let's do one where we work everything out. So you're given your function, x squared minus 6x plus 4 equals 0. Remember that all of these are reflexive, so that 0 could be on the left, and the x squared minus 6x plus 4 could be on the right. It doesn't change anything. We want to find its roots by making our table. So to make our table, we're going to find h and k. So it's the same table you've been making, it's just kind of turned on its side right now. So you need the opposite of b divided by 2a. So we get h is equal to 3. We're going to take that 3 and plug it in. So we have a vertex at 3, -5. If the table being sideways messes with you, you can draw it down below the normal way. The reason I did the table this way though was because I was going to put my normally top of my table in the middle of my table. So then this would be my +1s for my H's. And then these are like the YA plus K. So here would be like 1 times A, which is 1, so 1 times 1, plus K, which is -5. So 1 minus 5 is -4. And then the next one, so it's 0, 1, 4. So 4 times 1 is 4. 4 minus 5 is -1. And then your next one's at 9. 9 times 1 is 9. 9 minus 5 is 4. So the reason I put my vertex in the middle is because you can also count down equally, and then all of your y values repeat. We see that when we graph. So you have 3, -5, 4, -4, 5, -1, +2, and 6, 4. You also see in your table, this is your y-intercept, which you could have also seen from my graph up there. So when you graph or connect these points, you should see the same thing that the table shows, that I have a root between 0 and 1, and a root between 5 and 6. So you have that root between 0 and 1, as well as between 5 and 6. Great. I'm adjusting some of the problems on your homework to make the numbers nicer. So I had done the problems and I was like, So I'm going to scratch out 1, 4, and 5. So let me tell you what replacement equations you need. I thought about recopying them, but then I felt like a tree filler and staple waster. I kind of figured you could just cross them out just as easily. So whoa. It's drawing everywhere. You're going to scribble over that problem number 1, and you are going to change it to -2x² minus 4x plus 6. And just to give you an idea for this one, these are nice, pretty numbers. You do not need a calculator. For the next 2 problems, I'm going to leave them, but I'm going to tell you now that this is going to have decimals
And if you want to save yourself some headache, you can use a calculator to make your table. They'll still plot nice enough, but you could use a calculator to make your table. And then on the back, 4 and 5 will be no calculator again. But 4, we're going to change that equation to practice FOIL. I'm going to give you x minus 2 and x plus 4. So again, it's going to be really nice, pretty points. And then, because this one I put in our notes instead, we're going to change that one to 2x squared plus 4x minus 5. The rest of them can stay. They're actually your textbook problems, the first 5 I had written. So these ones can stay. You're just looking at the graphs and they gave you the equations and you're literally telling me how many solutions and where.